Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. This is actually a continuation in a lecture on in differential calculus on optimization. And in this question, we're being asked to maximize the volume of a cone inscribed in a sphere of radius 1. And recall from a previous lecture, the lecture right before this, all the methods for solving optimization problems. So let's go ahead and just really hop back very quickly. Or I should say hop back very quickly, not really hop back. Anyway, the steps here are just to read the problem, create a level of understanding that you can grasp, reword. That might involve rewording it or drawing it. The problem we're given actually is it's not very wordy. Label any unknowns, specifically what we're going to optimize. We want to optimize the volume, maximize the volume, and then create a master equation and so on and so forth. So let's go ahead and go through and do these steps. Now I've read the problem. It's actually pretty straightforward, except for some people might have a problem with this word inscribed. Inscribed just means that you have a cone that's set within a sphere, and the apex of the cone and the edges of the cone are kind of touching the sphere. So what I'm going to do is draw a picture of this situation. I'll pause the video while I get a decent drawing going. It's actually not too bad for me. And let's see, we have a sphere and there is a cone within it. And you can see that this cone is within the sphere. The edges of the cone are the apex and the corners of this cone are touching the sphere right here, here, and here. And I'm making the assumption that it's below the halfway mark of the sphere. However, that's not something that's fixed. We can actually change that if we want to. And we're told one thing about the sphere. It's a sphere of radius 1. That means that from the center here up to the edge, that distance right there is a distance of 1. Also from this center down to this edge right there is a distance of 1. And that's going to be important for us. So here's a picture of my my situation. I'll probably actually draw in an additional altitude down to the floor of this cone here, and I'll call that additional height h, because we just don't know how far down that is. Okay. I don't think there's anything else we need there. So we've read it. We have redrawn it or put it in a framework that is more familiar to us. And now I'm going to label the thing that I want to optimize. So I'm label the item that they tell me to optimize. They want me to maximize the volume. So I'm going to maximize the volume. And all we need is a formula for the volume of a cone. And you can actually look that up. It's just 1/3 pi little r squared times the height. Since I'm already using little h here, I'm going to use big H for the height. Okay. So that we want to maximize. Now notice, as I mentioned before, that when you create the master equation, and this is actually the master equation here, by the way, master equation, the thing you want to maximize, that you will often have more than two variables, and we need a relating equation, an equation that relates at least two of those variables together so that we can crunch this down to a relationship between only two variables. So the relating equation here takes a little bit of creativity, not too much though. Relating equation. I need some way to relate capital H here and little r squared. Now take a look at our picture. I'll zoom into it here. This picture right here, I'm going to say that the little r is, well, for volume of a cone, little r is the base, the radius of the base. So I'm going to go ahead and call this little r down there. And the overall height is actually just 1 plus h. So let's go ahead and go back to the normal view here. Let me scoot over. Okay. And actually, I don't even need to mention that the overall height is 1 plus h yet, even though it technically is h. The overall height of the cone is 1 plus little h. But I do have a relationship between little r and little h. The relationship is the Pythagorean Theorem. I know that 1 squared is little r squared plus little h squared. And so notice that I can now make a relationship between little r and little h. I also can make a relationship between big H and little h. This guy right here will be traded out for this stuff. And then the r squared I'll trade out for a 1 minus h squared. Let me go ahead and write that in. R squared is the same thing as 1 minus h squared. So that r squared, I should have used a different color highlighter, that r squared will be traded out for a 1 minus h squared. So inserting those in there, we get, so those, by the way, are the relating equations, the things that we can kind of use to compress our function down, our equation down. We now need to optimize v equals 1/3 pi. Instead of little r squared, we have a 1 minus little h being squared. And then instead of a capital H, we have a 1 plus h. And now notice there really are only two variables in this equation, a capital V, which we want to find the maximum of, and little h. And you can clean this up a little bit, right? This is the same thing as 1/3 pi, and you can distribute through all that stuff. If you do, you'll get a negative h cubed. Let's see, minus h squared plus h, and then finally plus 1. Now, we want to find when this volume function is maximized. We're going to use calculus. So maximize this. We're going to find out what dv dt is. Sorry, not dt, dh. dv dh. Basically, what's v prime? It's equal to 1/3 pi, and then derivative is negative 3h squared minus 2h plus 1. Double check my mathematics there. So I happen to know that I have candidates for local maximums and local minimums when v prime is equal to 0. So v prime is 0 when this polynomial, negative 3h squared minus 2h plus 1, is equal to 0. And I dislike personally dealing with negatives as my lead coefficient, so I'm going to go ahead and clean this up a little bit. Let's see if this factors. It might. Little guess and check action here, 1 and a 1. Let's see, one of those is going to be negative, and I'm going to say it's a positive and a negative there. Double check my work, and it does work out. So there we go. We have either h is 1/3 or h is a negative 1. Now, very, very, very often when you're dealing with optimization problems, you're going to get candidates for when v prime is 0, or when your function, the derivative of your function is 0. Or maybe I should say candidate critical numbers. Candidate critical numbers. These candidate critical numbers that you get suffer from reality. You need to look at the reality of these numbers. Is it realistic for h to be 1/3? And is it realistic for h to be negative 1? Remember what h is in this picture. H is the distance from center to either how far down you've moved the bottom of the cone or how far up you've moved the bottom of the cone. So if h is a negative 1, you literally have pushed this height all the way up to the top here, and your cone is literally at just a point hanging at the top of your sphere. So obviously you cannot maximize the volume of your cone by squishing it all the way to the top of your sphere. On the other hand, h could be a positive 1/3 just from the reality that our radius is 1. So we do have some length that we can add on to h from the center to get an extra 1/3 below the center. So I'm going to throw out the negative 1 And now remember, when you're trying to find, although that negative one's going to hop back in a second, when you're trying to find absolute maximums or absolute minimums, you have a closed interval. So my function again is v, and v is defined, the volume function is defined for h being anywhere from actually a -1 to 1. Now again, let's go back and see why. H is that additional height. H could be a -1. If it's a -1, that means we just have a point in space. If h is a +1, that means we've lowered this, the bottom of this cone all the way to the very, very, very bottom of the sphere. And when you do that, you'll get a cone that is a stick, essentially. It's no longer a cone. It's just a very long line. And so in that case as well, you're going to find out that it is not, that the area is definitely not, or the volume is not maximized. But to be rigorous about it, we'll make a table of values, h versus volume, and we'll plug in the end points of this closed interval and also our critical numbers. And let's see, if h is -1, what is the volume? So let's go back to the volume formula right here. Right? And if you plug in a -1 in that, you'll get 0. You could test it out. Let me just make sure I'm not lying to you. Negative, positive, negative. Yes. So when you plug in -1, you get a volume of 0. When you plug a 1 in, actually, you get a volume of 0. When you plug a 1/3 in, you get a 1/3 pi times the quantity. And then let me just plug in a third. Negative. Actually, you know what? Where I could plug that in? I'm going to plug it into this version of it. 1 minus 1/3 squared, which is 1 minus 1/9, actually, times 1 plus 1/3. Let me just double check that that was the formula. So I'm plugging it into this version right here. So 1 minus the height squared, 1 plus the height. And you see that's right there. And we're going to go ahead and simplify this. So this is going to be 4/3 right there. And this is 8/9 right here. Right, and let's see, so we have something over 81. The something is going to be 32 pi. 32 pi over 81. So that is actually the maximized volume. We know that that is the maximum value of these possible values. The minimized values are occurring when h is -1 and 1. But we know we can maximize the volume of this cone as long as we let the h be 1/3, or in other words, this total distance here be 4/3. Here you go. That's how you do an optimization problem. Again, step by step is really just reading it, developing a good picture to help you out. The picture really helps out in this situation. And from that point, making sure you write a formula for the variable you want to optimize. You have too many variables in that formula, and so you need to find a relationship between them, which we did. And then use material from previous sections in your textbook, which would be optimization, absolute maximums and minimums, to find the derivative of this function and the values of that function at the edges of the domain. And take the maximum if you're maximizing, or the minimum if you're minimizing. All right, I hope that helps out. Stay tuned. There'll be another video in a little bit.